In episode 89, titled Regression Families, When Linear Regression is Appropriate, we focus on how to choose a regression model by matching assumptions to the behavior of the target you are trying to predict.
Regression is often treated as a default choice whenever numbers are involved, but disciplined practice requires asking what the target represents, how errors translate into cost, and whether the underlying relationships are likely to remain stable.
Linear regression, in particular, is frequently misunderstood as either too simplistic to be useful or universally applicable because it is familiar.
The truth sits in between, and the exam expects you to recognize when linear regression is the right tool and when it is not. This episode builds that judgment by grounding model choice in assumptions, interpretability needs, and the nature of the problem rather than in habit.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series.
Regression is appropriate when the target you are predicting is continuous, meaning it can take on a range of numeric values rather than falling into discrete categories. Examples include price, demand, time to complete a task, latency, or resource usage, where differences in magnitude matter and error can be measured meaningfully. In these cases, the cost of being wrong is often proportional to how wrong you are, which makes regression a natural fit. Unlike classification, where the primary concern is whether a decision crosses a threshold, regression problems require you to care about how far predictions deviate from reality. This framing also implies that you should think carefully about the error metric, because different metrics emphasize different kinds of mistakes.
When the target is continuous and errors translate directly into operational or financial cost, regression provides the structure you need to reason quantitatively about those trade-offs.
Linear regression is most appropriate when the relationship between features and the target is roughly additive and stable, meaning each feature contributes a consistent marginal effect that does not depend heavily on the values of other features. Additive does not mean simplistic, but it does mean that the combined effect of features can be approximated by summing their individual contributions. Stability means that those contributions do not fluctuate wildly across time or across different regions of the feature space. When these conditions hold, linear regression can capture the dominant structure of the problem without unnecessary complexity. This is why linear models often perform surprisingly well in mature systems where processes are engineered and controlled rather than chaotic. The exam angle here is recognizing that linear regression is not about forcing reality into a straight line, but about deciding when a straight line is a reasonable approximation.
One of the enduring strengths of linear models is how well they perform with small to moderate amounts of data, especially when interpretability is a priority. Because linear regression has relatively few parameters compared to more flexible models, it is less prone to overfitting when data is limited. This makes it a strong baseline and, in many regulated or high-stakes environments, a preferred production choice because its behavior can be explained and audited. Interpretability matters when stakeholders need to understand how changes in inputs affect outcomes, such as how price adjustments influence demand or how system load affects latency. Linear models provide coefficients that can be discussed in plain language, which supports governance and trust. The practical takeaway is that data quantity and explanation requirements are not afterthoughts, they are central to model choice.
Transformations can often make relationships more linear, which expands the range of problems where linear regression is appropriate. Many real-world relationships are nonlinear in their raw form, but become approximately linear after applying transformations such as logarithms, scaling, or normalization. For example, A multiplicative relationship between variables can become additive on a log scale, making linear regression a good approximation. The skill is recognizing when a transformation reflects a meaningful change of perspective rather than an arbitrary mathematical trick. Transformations should be motivated by domain understanding, such as diminishing returns or proportional effects, not by trial and error alone. When used thoughtfully, transformations allow linear models to capture curvature while preserving interpretability and stability. Linear regression is a poor choice when interactions dominate and effects are strongly nonlinear because additive assumptions break down. In such cases, the effect of one feature depends heavily on the value of another, or small changes in input produce disproportionate changes in output. Examples include threshold effects, saturation, and complex feedback loops, where linear terms cannot capture the true structure without extensive manual engineering. Trying to force a linear model onto these problems often results in biased predictions and systematic errors that show up clearly in residual analysis. While you can add interaction terms and polynomial features, doing so increases complexity and can erode the original advantages of linear regression. The exam expects you to recognize when the problem itself calls for a different family of models rather than excessive patching of a linear approach. When many correlated features exist, regularized regression becomes an important extension of linear regression rather than a departure from it. Correlated predictors can make ordinary least squares unstable, producing coefficients that swing wildly in response to small data changes. Regularization introduces a penalty that shrinks coefficients and stabilizes estimates, trading a small amount of bias for a large reduction in variance. This is particularly useful in domains like telemetry analysis or pricing models, where many features capture similar information. Regularized linear models preserve much of the interpretability of linear regression while addressing practical issues of multicollinearity. Understanding when to apply regularization is part of using linear regression responsibly rather than abandoning it prematurely. Practicing regression choice across common scenarios helps solidify this judgment. In pricing problems, where small changes can have predictable effects on revenue and demand, linear or regularized regression often works well because relationships are engineered and monitored. In demand forecasting, linear models can be effective when seasonality and trends are accounted for through features or transformations, especially when interpretability matters for planning. In latency or performance modeling, linear regression can approximate how load, configuration, and resource allocation contribute to response time under normal operating ranges. In each case, the question is whether effects add in a stable way and whether deviations from linearity are small enough to tolerate. The correct choice is not universal, but it should be defensible given the structure of the problem. Evaluation metrics for regression should align with business tolerance because different metrics emphasize different aspects of error. Root mean squared error, for example, penalizes large errors more heavily, making it appropriate when outliers are especially costly. Mean absolute error treats all deviations linearly, which can be more appropriate when proportional error matters more than extreme misses. Choosing a metric is not a technical afterthought because it defines what the model is optimized to do well. A linear model that minimizes one metric may look less impressive under another, even though it performs better in practice. The exam expects you to connect metric choice to error cost rather than defaulting to whatever is common. Residual analysis is a critical diagnostic step for linear regression because residuals reveal whether the model's assumptions hold. Patterns in residuals can indicate bias, curvature, or heteroskedasticity, where error variance changes with the level of the prediction. If residuals show systematic structure rather than random scatter, it suggests the model is missing important relationships or that linearity assumptions are violated. Checking residuals is not about perfection, but about understanding where and how the model fails. This insight can guide feature engineering, transformations, or the decision to move to a different model family. A linear model that passes residual checks is far more trustworthy than one that simply reports a good aggregate score.
Communicating coefficients requires care because they represent marginal effects under specific assumptions, not universal truths. A coefficient describes the expected change in the target for a one-unit change in a feature, holding other features constant, which is a conditional statement.
This condition is often glossed over, leading stakeholders to interpret coefficients as simple cause and effect relationships. In practice, features may be correlated, transformed, or constrained in ways that complicate direct interpretation. Clear communication includes stating the context, the assumptions, and the range over which the interpretation is valid. Doing so preserves the value of interpretability without overselling certainty.
Avoiding causal claims is essential unless the study design explicitly supports causal interpretation, such as through controlled experiments or strong identification strategies. Linear regression is often used for prediction, not for causal inference, and conflating the two leads to incorrect conclusions. A predictive coefficient indicates association within the data and model, not that changing the feature will cause the outcome to change in the same way. This distinction matters in policy, pricing, and security decisions where interventions have consequences beyond prediction. The exam reinforces this boundary by testing whether you can separate descriptive modeling from causal reasoning. Maintaining that separation is part of professional rigor.
The anchor memory for episode 89 is that linear regression works when effects add, remain stable, and can be explained. Additivity ensures the model structure aligns with the problem. Stability ensures the learned relationships persist across time and conditions. Explainability ensures the model can be governed, audited, and trusted by stakeholders. When these three conditions align, linear regression is not a compromise. It is an appropriate and often optimal choice. When they do not, forcing linear regression creates risk rather than simplicity.
To conclude episode 89, titled Regression Families, When Linear Regression is Appropriate, consider one regression case and justify whether linear regression fits. Suppose you are modeling service latency as a function of request volume, server count, and configuration parameters within a controlled operating range. The target is continuous. Errors have measurable operational cost, and the effects of load and capacity are approximately additive and stable under normal conditions. Linear regression, possibly with regularization and transformations, is justified because it provides interpretable coefficients and reliable predictions within the expected range. In contrast, if you were modeling system behavior under extreme overload with cascading failures and nonlinear feedback, linear regression would be inappropriate because interactions dominate and stability breaks down. Being able to articulate that justification shows you understand regression choice as a matter of assumptions and behavior, not convenience. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.